Okay, so last time we talked about the eddy diffusivity of momentum and the eddy diffusivity of heat transfer, and basically these were the equations that we ended up with. Then this is the momentum equation. You can see it's written in terms of this eddy diffusivity of momentum that is related to turbulent transport. So it's related to this turbulent mixing term. And we have the eddy diffusivity heat transfer here, which is related to turbulent transport of energy, so related to this turbulent transport term. And we also said that if we want models of these quantities in the literature, you're going to find that they're written in terms of what are called inner coordinates, so y plus and u plus, and inner temperature is theta plus. So today we're going to talk about what these inner coordinates are, and how they're defined and why they're defined that way, right? So rather than just give you the equations and say this is y plus, this is u plus, we're actually going to look at why y plus and u plus are defined the way that they're defined. So inner coordinates are defined based on the length scales and the velocity scales and the temperature scales that are important for a turbulent flow, right? So if we want an inner coordinate or an inner length, like a y plus, which is going to be a dimensionless y, where y is the distance from the wall, we're going to normalize that length value by a length scale, and we're going to use the length scale that's most important for a turbulent flow. So the length scale that's most important for the turbulent flow is basically how big approximately is the viscous sublayer. So we're going to call that L sub characteristic Vs for viscous sublayer. So y plus is y divided by our estimate for how big the viscous sublayer is. All right, so this kind of goes back to when we talked about turbulent flows and how the important length scale in a turbulent flow is not the boundary layer thickness. That doesn't really govern much of anything, but rather the viscous sublayer thickness, because that's where all the temperature gradient is occurring. That's where all the velocity gradient is occurring. So velocity scale, similar kind of thing. We're going to take our velocity and we're going to normalize it, divide it by the important velocity scale for turbulent flow, which is not the free stream velocity, but rather the size of the velocity fluctuations, right? Because it's those velocity fluctuations that are driving the turbulent transport. So u plus will be u bar divided by u star, and u star here is our best estimate as to how big those velocity fluctuations are. And then finally, temperatures. I think I've said several times, hopefully you've heard it, that to take a temperature by itself and non-dimensionalize it is kind of silly. You always want to be non-dimensionalizing temperature differences relative to another temperature change or temperature difference. So our non-dimensional temperature, theta plus, is going to be the difference between the surface temperature and the average temperature. So that's the temperature difference relative to the surface. And we'll normalize that by T star, where T star is the approximate size of the temperature fluctuations that you see in the flow. So in order for us to actually do this and make these definitions, we have to understand what L characteristic Vs is, what U star is, and what T star is, right? We have to make these estimates. And so, what we'll spend the rest of this lecture doing is actually coming up with estimates for these things so that you see where these definitions come. All right, so let's start with trying to estimate how big the velocity fluctuations are. So how big is this U star term? And at least one way of doing this is you go back to our Reynolds averaged equations, which is this guy right here, and you recognize that this term is the apparent shear stress, right? So this is the shear stress, the total shear stress, which is composed of the viscous shear stress, and then this is the turbulent or the Reynolds stress, right? So if we're outside of the viscous sublayer, we're still really close to the wall, but we're just beyond that viscous sublayer. we're into a region where we have these turbulent eddies and they're helping us transport momentum, and therefore this term, the second term, is going to be much bigger than this first term. So we're into a region where at least approximately we can write that the apparent shear stress is mostly made up only of the turbulent shear stress. And then we can come in and try to estimate the scale of either side of this equation in order to come up with an estimate for U star. So this side, the left side, is the apparent shear stress. Our best estimate as to what that apparent shear stress is the shear stress felt by the surface. So we'll call that tau s, the surface shear stress. And then if we come on this side, we are integrating two velocity fluctuations together, right, with respect to time, and then dividing by time. So we said at one point already that the scale of the u velocity fluctuation and the v velocity fluctuation are pretty similar, right? So even though the magnitudes of those two velocities are very different, the scale is the same. They're going to fluctuate about the same. So this term is about equal to u star squared, right? The magnitude of the fluctuation. We're integrating u star squared over time, so that's going to be u star squared times time divided by time. So this right side is going to be order of magnitude rho times u star squared. So if we just substitute tau s into the left side and rho times u star squared into the right side, we get the shear stress at the surface is approximately equal to rho times u star squared. And if I solve this for u star, then I get that u star is the square root of tau s over rho. So this is our estimate, our best estimate without measurement or math, of how much the velocity will be fluctuating in a turbulent flow. If we move forward one slide here, we're going to call that, or actually people do call that, the eddy velocity. So when they say the eddy velocity, they're really talking about this u star term. They're talking about basically our best estimate as to how much this velocity is fluctuating. So this black line is the actual velocity. We talked about how we have an average velocity, the magnitude of the oscillation of the actual velocity about the average velocity. Our best guess for that magnitude is u star, right? It's the amplitude of these fluctuations. So our inner velocity then, u plus, is just going to be u bar, so that velocity normalized by u star. So u plus is u bar, and now I have an estimate for what u star should be, so we'll divide it by the square root of tau s over rho. So that's our inner velocity, right? That's what u plus is defined as. The next thing we should do is try to get some kind of an estimate as to how big the viscous sublayer is, because that's our characteristic length scale, right? So same idea, right? We go back to our Reynolds averaged equation. We come over here and we say this term right here is the apparent shear stress. Again, it's made up of a viscous component and a turbulent component. Last time we said, well, what happens if we get outside of the viscous sublayer? And we said only this term is important. This time let's say, well, what happens if we stay inside of the viscous sublayer? So inside of the viscous sublayer, we would expect only this term to be important, because the turbulent eddies go away, right? I mean, that is what actually defines what a viscous sublayer is. So inside the viscous sublayer, we can just keep this first term, and we can see where that takes it. So if I just keep this first term, then inside the viscous sublayer, I'm really close to the wall. So for sure, I have the apparent stress is the shear stress on the surface. So that's then mu times du dy. I can separate this, so I have du on one side, I have tau s over mu dy on the other side. I'll integrate both sides, so this tells me then that if I start at u equals 0 and go to u, and over here I'm going to integrate from y equals 0 to y, I get this linear velocity distribution inside the viscous sublayer. So inside the viscous sublayer, where the viscosity is only the molecular viscosity, I would expect a linear velocity distribution, right? So how does that help us estimate how long that linear velocity distribution persists, right? How does it help us estimate how large the viscous sublayer is? Well, here's a plot showing that linear velocity distribution in the viscous sublayer, right? So y equals 0, u equals 0, that's this point right here. And then as I move away from the wall, my velocity increases linearly, and at some point it stops increasing linearly, and at that point I am beyond the viscous sublayer, right? But as long as it's increasing linearly, here's my equation for how the velocity distribution grows. So one way of thinking about how big this viscous sublayer is by remembering that we have these velocity fluctuations that we've already estimated, right? We said that when turbulent eddies are present, the fluctuating component of the velocity, that eddy velocity, is the square root of tau s over rho. So it's pretty clear that you can't get a fluctuation that's that big until you at least have a velocity that's that big, right? I cannot fluctuate 10 meters per second around a velocity that's only 1 meter per second, right? So what this is saying is that the size of the viscous sublayer is basically as large as it needs to be so that the velocity grows to the point where you can get the velocity fluctuations that we know have to happen when turbulent eddies are present, right? So here, I'm just going to say, at the point where U bar reaches U star, right? So that's this point right here. That's where Y is at least approaching the size of the viscous sublayer, right? So that's just basically going back into this equation right here. And for U bar, I'm going to substitute in U star. And for Y, I'm going to substitute in the characteristic length of the viscous sublayer. So that's this. If I solve this for L characteristic Vs, I get this estimate for how big the viscous sublayer must be in terms of U star, which is something we've already estimated, right? So that's our characteristic viscous sublayer length. We have that right here. Again, just to physically indicate what that means, this is basically our best estimate as to how thick this layer is next to the wall where there are no turbulent eddies. And when we start looking at data, we'll see that we did okay, but we missed. In fact, this layer is about 4 or 5 times bigger than what we estimated here. But it's a reasonably good scaling that we just got. So our inner coordinate, our inner position is y plus, and it's just y. So the distance from the wall normalized by this length scale that we just got, L characteristic Vs. So y divided by U star times mu, and then over tau sub s. All right, so we have U plus, and we estimated U star to get U plus. We have Y plus. We had to estimate L characteristic Vs to get Y plus. We have one more, which is theta plus, right? I have to estimate T star to get theta plus. And the way we do that is basically exactly the way we did our estimate for U star, except for in this case, we're going to start with our Reynolds averaged energy equation. And I come over here and look at this term. This term is the apparent heat flux. And again, it's composed of a molecular transport of energy, which is Fourier's law, and then this turbulent transport of energy, which is given by this integral here, right? So just like we did for U star, we're going to say, okay, if I am outside of that viscous sublayer, then I'm getting into a region where this molecular transport of energy, it doesn't disappear, it's just not very important, right? It's being dominated by the turbulent transport of energy. So at least approximately my apparent heat flux is entirely made up of the turbulent component here, right? And so again, I'll try to estimate both sides of this equation to come up with a scaling for the size of these temperature fluctuations. So on the left side, I'm still pretty close to the wall. The heat flux is going to be the heat flux at the surface of the wall. This is my convection heat transfer rate, or at least heat transfer rate per unit area. That's what I'll plug in here. On the right side, what am I integrating here? I'm integrating a velocity fluctuation times a temperature fluctuation. So the scale of my velocity fluctuation is obviously U star. The scale of my temperature fluctuation is the thing I'm trying to estimate, so T star. So this side here is going to be rho times C times U star times T star. And then I'm integrating with respect to time and dividing by that time so the times go away. So if I plug this into here, I plug this into here, I get this equation here, right? The heat flux at the surface is rho c u star times t star. I can solve this for t star. That is my eddy temperature fluctuation, right? This is about how large I would expect the temperature fluctuations to be in a turbulent flow. And so if this is temperature with respect to time, this black line is the actual temperature. It's fluctuating around an average temperature T-bar, right? And the size of these oscillations, the scale here, is T star. So T star is given by this. And if I want my inner temperature then, theta plus, it's just the temperature difference relative to the surface divided by or normalized by the size of these temperature fluctuations, right? That's this equation right here. Okay, so now we know what these inner coordinates mean. When I see a y plus in my mind, I know, how that's defined, what that really means. When I see a u plus here, the same thing. And that gets me to a point now where I can at least think about using these models to actually solve for a velocity distribution and a temperature distribution using our Reynolds averaged equation. And I guess just to be clear, these are all models for the eddy diffusivity of momentum, so we would plug those right into my x momentum equation, right? Because that appears there, that's our turbulent viscosity. When I look at my energy equation, I need the eddy diffusivity of heat transfer in order to get a turbulent conductivity. But we said that the Prandtl number, the turbulent Prandtl number, is always something like 0.9, right? And so if I know that the turbulent Prandtl number is very close to 0.9, then if I have a model for the eddy diffusivity of momentum, I also have a model for the eddy diffusivity of heat transfer. So I can use any of these. I can use any of these models to get either one of these two quantities, and that's what we'll do next time. We'll start thinking about simplifying our Reynolds averaged equation to be applied very near the wall in what's called the Couette region, and then introducing these models for the eddy diffusivity of momentum and heat transfer in order to actually get a solution. And those solutions are called the law of the wall, right? The law of the wall is nothing more than just a sort of a really grand name for a really pretty simple thing. So we'll do that next time.